Question number 1. Two straight vertical wires X and Y passes through holes in a horizontal card. This is given in the figure 8.1. And this figure shows the card view from above. We have two vertical wires, children, X and Y. And there is a current in each wire in downward direction, means into the page. Downward direction, children, into the page. Now, what do you need to calculate? The magnetic field at Y, due to the current in X, produces a force on Y. Magnetic field at point Y due to current in X produces a force on Y. Then place a tick in each blank column of the table to indicate the direction of this magnetic field and the direction of the force at point Y. You have to find out, children, direction of the magnetic field at point Y and the direction of the force at point Y. So think about this question, children. Take some time. We have a vertical wire X. We have a vertical wire Y. In the question number 1A part, they said the X conductor carrying current in the downward direction. Actually, both the conductors are carrying in the downward direction, X as well as Y. In what direction? Into the page. Look at your notebook, children, that current is entering into your notebook, means from upward to downward direction, from ceiling to floor. That is the meaning of this statement. Or if you're looking the statement, if you're looking this question in the laptop screen, so it means that the current is entering into the laptop screen. After that, let's see what is given in the box down. Magnetic field at Y. Okay, let us find the magnetic field first, children, at point Y. So if you recall, children, consider this situation that I have this wire carrying current downward. If current is downward, first, children, draw the magnetic field patterns. Magnetic field patterns, we know concentric circles. 1 circle, 2 circle, 3 circles, 4 circles. So around conductor X, there will be a magnetic field. And the magnetic field is around the conductor X. And suppose this is the point Y, that point Y or the conductor Y is in the magnetic field produced by X. So recall the part, children, that we have discussed in last class. If we placed a conductor where in a magnetic field produced by another conductor, so that conductor will experience a force that is given by the Fleming's left-hand rule. So we will also calculate that force. But before that, find out the magnetic field at point Y. So this is point Y, children. This is the same question, children, that we have discussed last time. Conductor, current downward, point P. Now here point Y, it is to the right side. Use the right hand grip rule, or right hand palm rule, actually. Right hand palm rule. So at point Y, you know what is the right hand palm rule? Current is moving downward. Thumb should be in the downward direction, in the direction of current. Current is entering into the plane of the notebook. Thumb into the downward direction. Y is to the right hand side. Y is to the right hand side. Y point. And at the palm side, you have to look at the palm, children, and you have to draw a perpendicular. That perpendicular will give you the direction of magnetic field at point Y. And I can see here, if the current is entering into the plane of the paper in the inward direction. Now let me show you the paper. This is a paper. This is your notebook. Current is entering. Point Y is to the right hand side. And I can see that the perpendicular at point Y is coming in this direction. So in this direction means towards me means, let's say, as per the options. What the options are given. Towards the top of the page. No, this is not the top of the page. Towards the bottom of the page. Is the magnetic field at the bottom of the page? To the left side, to the right side, into the page, out of the page. Now children, please, whoever finds this answer, please tell me where is the direction of magnetic field at point Y? Where should I put a tick mark? Abhishek, Himanshi. I have explained the rule. You need to apply it. Ananya said magnetic field is bottom and the force is to the left hand side. And there is one more answer. Oh yeah, okay. Ananya. Other children, Ethan. If you draw the diagram on your notebook, or if you see it, and if according to the laptop screen that now children, I have to just move a little. Current is entering my laptop screen into laptop screen. Point Y is to the right hand side at the tip. At the palm, you need to draw perpendicular. Perpendicular is coming downward. Downward means at the bottom of the laptop screen. Where is that option at the bottom? At the bottom. Now, if I see here, children, I find that the answer is towards the bottom of the page. If the magnetic field at point Y is at the bottom of the page, find out the direction of force, children. For the direction of the force, you need to apply Fleming children, Fleming left-hand rule. Left-hand rule. Find the Fleming left-hand rule, children. I told you, father, direction of force, mother, magnetic field, child, current. Magnetic field is where we have find in the bottom of the page. So this finger should point the bottom of the laptop screen. Current is entering into the laptop screen. So the middle finger, it should point in the laptop screen. Still, my first finger is downward in the direction of magnetic field. The second finger is towards the laptop screen. Current is entering, and look at the thumb. Here I can see that the thumb is going, children, to the left-hand side of my left-hand side, children. It is to the left-hand side. So left option for the force is here. So you need to click here. Now, children, is there any doubt? Tenth class students. Are you here or you not, or you're sleeping, children?
We are here, sir.
So you're not replying, you're not responding, you're not sending your answer in chat box. You have to prepare these questions. You have to prepare. These are the important questions. Now, next one. State and explain whether there is also force on wire X. State and explain whether there is a force on wire X. Where is X? Where is Y? Children, look at the figure. Because they said, what they said, both are conductor carrying current in downward directions. So conductor, around conductor X, there is a magnetic field. Around conductor Y, there is also a magnetic field. So it means conductor X and Y, we can't intersect actually. Both conductor X and Y are placed in the magnetic field produced by each other. If rule is applicable at point Y due to the conductor X, so similarly the rule is also applicable that the conductor X is also placed in a magnetic field produced by the current carrying conductor Y. So that's why you have, that will be your answer, children, that conductor X will also experience a force. Conductor X will also experience a force due to the current is moving in a conductor Y, and then the point X will be in the magnetic field produced by Y, conductor Y. They have not asked about that. What about the magnetic force acting at point X? If they ask, children, then again you have to find the magnetic force and the magnetic field at point X by using the right hand rule, right hand grip rule, and right hand palm rule actually. And for finding the direction of force, you need to apply Fleming left hand rule. Transformer topic, children, we have not done in class. So once we're done, then we will come back to this question. So I'm not doing this one. Question number 2, children. A teacher suspends 2 pointers in a magnetic field. One pointer is made of brass. Brass is a non-magnetic material. And the other is a magnet. She holds the pointer in the initial position shown in the 2 upper circles of figure 7.1. This diagram 7.1. She then releases the pointers, and then what happens? In the lower circles of figure 7.1, draw the settled final position of the 2 pointers. Now look at the statement here carefully. Look at this statement and this diagram. This is the brass pointer. Where is this brass pointer? This brass pointer is placed in a magnetic field. These arrow signs are representing the magnetic field. And North pole is here, South pole is there. Magnetic field lines, they move from north to south. Similarly, for on the right hand side, we have a magnet whose north pole is pointing in this direction, south pole is this. Draw the final position of the brass pointer in the circle. What happens, children? The brass pointer is dropped or moving in the magnetic field. It's a non-magnetic material, so it won't experience any kind of force, any kind of magnetism, or any kind of deflection. So finally, that you can draw the same diagram, actually the same pointer, the same arrangement. Okay, so that you have to draw the same diagram, that the brass pointer will remain same in the horizontal position. But what about the magnet? Magnet that you can consider that it's a magnetic compass. So north and south pole is there. Magnet is placed in a magnetic field that is a uniform, or even you can put more lines here. These are the diagram like that. And if the magnet, how this magnet will settle? And we know, children, that magnet in a magnetic field or magnetic compass, it will move or it deflect, means it will try to keep its north pole in the direction of magnetic field. So the north pole will deflect and it will try to go in the direction of a magnetic field. And so magnetic field north here, south here. So this arrangement will be like this, children. So north pole of the magnet will align itself in the direction of magnetic field. Please remember, as we have studied in the electricity chapter, children, if you recall that if we place a positive charge particle in electric field, so that positive charge particles will experience a force in the direction of electric field lines due to the positive charge. The same concept here. Magnet is there. North pole we will look. North pole will point. align in the direction of magnetic field. I hope this part is also clear, children. And this is the A. In the lower circle, you need to draw. Explain the final position of the brass pointer. Now, in B1, you need to explain why the brass pointer is keep pointing in the horizontal direction. There is no change. Then you can explain it's a non-magnetic materials. It won't experience any force in the magnetic field. That will be the explanation for B1 children. In B2, explain the final position of the magnet. As I told you earlier, final position vertically, North Pole will be in the upward direction, in the direction of the magnetic field. So remember this part, children. Suggest the material from which the magnet is made. You have to find out the name of the magnet. What material is used to make a magnet, children? To make a temporary magnet, we use iron. To make a permanent magnet, we use steel. And there are many, many other magnetic materials actually. You can write any one name. I want to discuss also, children. Then the remaining question I will give you that you can practice by yourself. Question number 3. And here a vertical current carrying wire passing through a car at X. There's the same like question number 1, children. Again, they have not given the top view of the current carrying wire, but now they have given a diagram, complete diagram. Conductor carrying current in the downward direction, again entering into your notebook, means from ceiling towards floor. And on figure 8.1, sketch on the card the pattern of the magnetic field produced by the current in the wire. You have to draw a pattern, children, actually. Current is downward, children. So may I know the answer from Fio? Fio, please. Can you tell me? Let me allow you to annotate. And if you can draw the magnetic field patterns around this current carrying wire X. Fio, please. Okay, good. One more circle, please. One more. Yeah, okay. Thank you, Fio. So this is the first part of this question, children, that we need to draw what? Concentric circles. Magnetic field pattern, we know that it is a concentric circles, but you know the better diagram is you need to make a space. As we know, magnetic field, strength of magnetic field decreases as we move away. And if you look carefully, children, in this circle that Few has drawn, the gap from the conductor is looking almost same. This is looking same, but when you draw these circles, children, in exam, remember there should be increase in spacing as we move away from the conductor. Because let's see the second part of this question, then you will understand. The detail of your sketch should suggest the variation in the strength of the field. Variation in the strength of the field. So let me erase this circle and want to draw by myself. First one, children. Then the second, increase the gap. And the third, then there should be more gap. And that more gap, it represents the field is weak. I'm not saying that the previous diagram was wrong, but that was correct. But remember, children, try to make a certain increase gap in between the circles. You know, the concentric circle, their radius should increase and increase. And so here, okay, after drawing this concentric circles, you need to draw the direction of magnetic field. To draw the direction of magnetic field, children, what rule I have suggested you? Right hand grip rule. Current downward, just you have to rotate, curling of fingers. And I see here current is downward and the curling of fingers is giving me the direction of the magnetic field in the clockwise direction. So if you have drawn 3 circles, so you need to put at least one arrow in the clockwise direction on each 3 circles. So this is our question number 3, A part. We are done with show the direction of magnetic field with arrows. We have done. The details of your sketch should suggest the variation in the strength that you have to show the spacings different, and then you will get 3 marks for 3 of these points. Question number B. Using your knowledge of investigating the magnetic field around a bar magnet, suggest an experiment or experiments to confirm that you have drawn the correct pattern and direction in A. Now we have to cross verify that the concentric circles will be there or not. Magnetic field will be in the form of concentric circles or not. So what experiment you will perform? Yajish, what experiment you will suggest?
Using a magnetic compass.
But with the help of magnetic compass, yeah, if you take a magnetic compass and if you keep pointing at different positions, so you will find that the magnetic compass north pole will point in the clockwise direction and you will get concentric circles. Okay. Any other experiment, Madeline? Madeline and Yash, please, any one of you? Any other experiment? If you want to read the statement, please do. Calista said that with the help of the iron filings, yes. On this wooden board near this current carrying conductor, if you put iron filling and tap the board, then you will find that the iron filling, they should align in themselves in the form of a concentric circles. Okay, let me move to the next part. Next question. A second current carrying wire is inserted vertically through the cardboard at Y. Suggest why there is now a force on the wire at X. A second current carrying wire is there at point Y. Already discussed in question number 1, but now in question number 3, they are asking the same concept. They're saying they have inserted another conductor, another long wire at point Y. At point Y, children. And then what happens with the conductor? What happened with the conductor, this conductor X? You know that due to the current in wire Y, again, children, magnetic field will be there. So it means I will consider that the conductor X is in the magnetic field produced by the conductor Y. Listen this explanation, children, carefully. In exams you have to write. So conductor X is now in the magnetic field produced by the conductor Y, and due to that, conductor X will experience a force. Again, children, they have not asked here in what direction the conductor will move, so you can practice by yourself in what direction that the conductor X will experience a force. Okay, C part is done. In D part, the wire at Y is moved to the another position Z. It still carries the same current. Tick the appropriate box to indicate whether the force on the wire at X is now smaller, greater, or same. The force on wire X at position X. Look the diagram. They have removed the conductor from Y and inserted at the point Y. Inserted at point Y, children. Same direction of current downward. Same amount of current. They have just changed the position. So what happens to the strength of magnetic force at point X, children? Yeah, there is one, I received one answer. And then I said, then it will be smaller. Yash, may I know the answer for this question from you? Yash Banner.
The force will increase.
you said the force will increase. Why this force will increase? Yes. Conductor X and conductor Z. Yes, your answer is wrong here. You have to, I think you need to study this concept again. Because if you are saying that the current magnetic field will increase, then it means there is a problem with the concept. You need to understand this concept. Now, children, another student, Sampan Malik. Sampan, conductor is removed from point Y to another position at Z. What is the effect or what is the strength of magnetic field at point X? Increase, decrease, or remain same? Sampan Malik.
Yes, sir.
Yeah, tell me the answer, please.
The magnetic field decreases, sir.
Reason with explanation, please. I need explanation here.
Cursor has moved further away from the center, so the current has been reduced.
No. Current is same. There is no change in current. Only the position of the conductor has been changed. Current is same, but the position of conductor is changed from Y to Z. It means you are unable to give answer. So it means students 10th class, you are not listening. Yeah, everything has been explained by me, but still you are unable to find out answer. Okay, let me move to the another student, Melvin. I want explanation, children. Melvin, please. You want to read the statement, you can see here. We are on question number C. Not C, but sorry, D part. Melvin, are you here or not? Melvin is not here. Abin Lee, please. Abin Lee, are you here?
Yes, sir, I'm here.
Yeah, please. Can you explain the answer?
It decreases
Yeah, answer is it is decreasing, but I need the explanation.
because it's farther away from the center of the magnetic force point, so it decreases.
Yeah. Very good. This is the simple answer, children, that as the point X is away from the point Z, and we know that there is a magnetic field around a current carrying conductor, straight conductor, and the strength of magnetic field decreases as we move away from the conductor. So now here the gap between X and Y and X and Z has been increased. You can see here it's increased. So then that's why the magnetic field is there at point X, but it will be weak or smaller compared when the conductor was placed at point Y. Explanation is very important, children. In exam, you can write your answers. You can find your answer from Google. But remember, in the future, during interview time, no company will select you if you are unable to give the explanation. Question number 4, children, that you try yourself. And okay, let me first pause this meeting.